Aw, yeah, it's geometry time. It's time to get ready for a test, you guys. Are you excited? Yeah, an opportunity to show off a little bit, to show me what you know. I'm here to talk a little bit about test strategy and go over some problems with you. So what we're going to do together is talk about the possible topics that are going to be on the test and then do some practice problems. What you're going to do on your own is dig into those notebooks. Use those questions that you've been writing yourself to quiz yourself on what's in your notes. Maybe rewrite your notes neatly, go over them. Maybe write some questions, maybe write some summaries. Studying for a test means that you're looking at your notes and you are digging into the information that's in there. Okay? So that's what you're going to be doing on your own to get ready for this test. And of course, any missing assignments that you might have, that's important to do. So here are the topics that I'm going to choose from for the test. What we have studied since our last test was translations, compositions, lines of reflection, reflection rules and glide reflections, rotations, dilations with positive scale factors, dilations with negative scale factors, and similarity transformations was the last thing. So make sure your table of contents includes all of these things and that you have notes for each of these things, because if you don't, you can still create them. You can go back to the Google Classroom, you can find the videos with these titles, you can watch those videos and take these notes. One of the good things about distance learning, and there aren't many, but one of the good things about distance learning is that you can always, all the time, have access to the learning that you need to do. Maybe it's 11 o'clock at night and you'd like to learn about rotations. You can do it. And I don't have to, get out of bed to help you. Anyway, these are the topics. Make sure you have notes for all of these because I might just ask something about any of this on the test that's coming up. All right, so what my role here is just to review with you as quickly as possible some of the concepts that you might see on the test. So when we first started talking about transformations, we started talking about translations. And translations come with vectors. Vectors describe movement, and we haven't done a whole lot of homework around vectors, but I just wanted to remind you that they exist. First of all, we can name a vector by starting at an initial point, noticing an initial point, and noticing a terminal point, and just writing them down. So we could name this vector JK, because J is the initial point and K is the terminal point, and then we need to put some kind of a symbol on top. It would be, you might think you'd want to put an arrow on top, which is kind of true, but an arrow on top would be a ray. And a vector and a ray are not the same thing, and so for a vector, we just put the top part of the arrow, and that is the proper name of that vector. We can also write it in component form, and that's an awful lot like writing a point. We're going to figure out how far it goes along the x-axis and how far it goes along the y-axis and throw those two components together. And so along the x-axis, it goes like that. So 1, 2, 3. And then along the y-axis, it does this. 1, 2, 3, 4. And so 3, 4 is what we want to write down. But if we wrap that up in parentheses, then that would be a point. And this is not a point, it's a vector. And so we want to use these guys here. And I still, to this day, cannot remember what they're called. I like to call them pointy bits. Oh, maybe I'll look it up someday. Okay. Then, once we started getting the idea of vectors, we talked about how we could translate using vectors. And vectors explain motion, how far that motion goes and in what direction. So the vertices of a triangle are there, and we're going to have to graph those, and then we're going to translate using that vector. So let's put these points down first. We've got 0, 3, which is here. That's A, and then we have 2, 1, 2, 3, 4 for B, and then C is at 1, 0, so right about there. Here's C. And this vector is telling us that this is how far we go in the x, and this is how far we go in the y. So that's a positive 5, so we'll move in the positive direction 5 units, and that's a negative 1, and so we'll go down 1 unit. So we're going to take A, and we're going to move it over 5 and down 1. So let's see, 1, 2, 3, 4, 5, and 1 to find A prime. B goes over 1, 2, 3, 4, 5, and down 1 for B prime, and C goes 1, 2, 3, 4, 5, and down 1 for C prime. And we have successfully translated that triangle according to the vector. So the next thing we did was start talking about translation rules, and we talked a lot about different types of rules, and rules end up starting with like this XY bit, and then there's an arrow, and then there's something that happens in these parentheses, and we're going to fill in that blank when we solve this problem. So writing a rule for a translation is just a matter of writing the rule for what happened. So when we look at, for example, point A, in order to get to point A prime, we had to travel like this, and then we had to travel like that. And we went in the left direction, or negative direction, 1, 2, 3, 4, so -4, and then we went up 1 to get to A prime. Did that happen with B? When we count B, we go 1, 2, 3, 4, and then up to get to B prime, sure. C, same thing, 1, 2, 3, 4 to the left, and up 1 to get C prime. So it appears that we have moved 4 units to the left and 1 unit up to translate this triangle. So because the -4 is our x component, we would write x minus 4 here. And then we went up 1 for our y component, so y plus 1, and there is your rule for the translation. It's just a matter of counting and writing it in the proper notation. Then we started talking about composing translations, where if we do one translation and then another, that we arrive at what's called a composition, or putting things together. And so we have a segment RS with endpoints R and S, and its image after a composition. And a composition is just doing one translation and then another translation. Okay? So we're going to do this one first, and the rule is to move your points 5 units to the right and 2 units down. So we're going to take S and move it 5 units to the right, 1, 2, 3, 4, 5, and 2 units down, 1, 2, and get S prime. We're going to do the same thing with R. 1, 2, 3, 4, 5 to the right, and 2 units down for R prime, and that is the first translation. Now we're not going to go back to the beginning. We're actually going to move from SR prime to get SR double prime by moving 4 units to the left and 2 units down. That's what that translation rule is telling us to do. So S prime moves 1, 2, 3, 4, 1, 2 to get to S double prime. And R prime goes 1, 2, 3, 4, 1, 2 to get to R double prime. And that is what the composition looks like. Now I'm going to get rid of this here because we want to write the composition rule. That's what we're truly after here. Well, the rule's always starting with, that doesn't look like an X at all. Let's try that again, Miss Waite. X, Y goes to, and then what does it go to? Well, we can combine these two translations to get our composition, and that's just a matter of adding things up. In other words, what is 5 minus 4? Positive 1. So we have x plus 1 here, and then what is -2 minus 2 more? -4. Done. And there's your composition rule. Is it correct? Did we move 1 unit to the right and 4 units down to get from SR to SR double prime? Well, let's see. S from S, 1 unit to the right and 4 units down. Yep. 1 unit to the right and 4 units down. And so we know we're in good shape. So that's how you deal with compositions. Let's see, from there we went directly to reflections, and reflections came with more rules, these coordinate rules to be specific. I'll make them a little bigger. And when I was typing, it's hard to get arrows in there, and so these always have arrows right here. And if you watch the videos, I had quite a discussion with you about when to use the rules and when not to, because part of, I think, learning math is knowing the most efficient methods at the right time. And so when we look at part A, we see that we have this triangle, and we want to reflect it in the line x equals 5. And remember that in is the same as over. But x equals 5 is a vertical line where x is 5. So let's see, 1, 2, 3, 4, 5. Here is x equals 5. Okay? Now we want to reflect in that line or over that line. Notice that's a vertical line. And also that there's no rule for it. So really all we have to do is do some counting. Because we have these little predictable distances, these little boxes that we can count, let's count them. So A is 1, 2, 3, 4 away from x equals 5. And so we want to count out 1, 2, 3, 4-ish out the other side to get A prime. B is right there on that line, so B and B prime are exactly in the same place. And then C is 1, 2, 3 away from x equals 5, and so 1, 2, 3-ish out the other side gives us C prime, and we have reflected, oh my gosh, Miss Wait, we've reflected that triangle over x equals 5. When you have horizontal and vertical lines, counting is a great way to get after this. But y equals x is not horizontal or vertical. It looks like this. It's all the points where the values of x and y are exactly the same. So 1, 1, 2, 2, 3, 3, 4, 4, negative 1, negative 1, negative 2, negative 2. This is a line. Y equals x. And I'm going to draw it very badly. But that's what that line looks like. Now that is not horizontal or vertical, and so we have to resort to the rules, but which one would we choose? Well, we're not reflecting in the x-axis, so we don't need that one. We're not reflecting in the y, so we don't need that one. And we're not reflecting in y equals negative x, and so we're going to choose the third rule. And what that rule tells us is take your points x and y and just flip-flop their values. So you need the values of that point. Well, A, as it says in the problem itself, is at 1, 3. So in order to get A prime, we just flip-flop those values, so we get 3, 1. B is at 5, 2, which means that B prime must be at 2, 5. C is at 2, 1, so C prime must be at, yep, you guessed it, 1, 2. And those are the new points that we will plot. So 3, 1 is where A prime is. 1, 2, 3, 1. Here's A prime. B is at 2, 1, 2, 3, 4, 5. I'm so sorry about this feedback, man. 2, 1, 2, 3, 4, 5. Here's B prime. And C is at 1, 1, 2. C prime. There you go. You have successfully reflected that triangle over y equals x using the rule, because you have to. From there, we also talked about using other rules. This is finding the coordinates of an image over y equals negative x, and you don't even need a graph for this because you've got the rules. Y equals negative x is this one right here, the last one, and what it tells us is that you not only take those values and flip them, but you also turn them to their opposite. These negatives in this rule do not mean that they stay negative. It means that they will be opposite. So they will be, if they were positive, they'll be negative. If they're negative, they'll be positive. So in other words, if we want to find the coordinates of fg prime, we can run f through that rule. F starts at negative 5, 4. But if we run it through and get f prime, we know we not only need to flip those values around, but we have to change them to their opposite. And so the 4 goes here, but because it was positive, it will now be negative. The negative 5 goes here, but because it was negative, it will now be positive. And there is the coordinates for f prime. Do the same thing with g. G lives at 3, 7. And to get g prime, we have to switch the values and turn them to their opposite. Negative 7, negative 3. Because they were positive, they will go negative. And that's how you use rules of reflection. Okay. And then we started putting these things together, and we have translation and reflection compositions where we do a few things at the same time, and it's just like compositions with two translations. You just do one thing at a time until you get the composition done. And so we start out at 3, 2 for A, 1, 2, 3, 2. Here is A. And then B is at 1, 2, 3, 4, 5, 6, 1, 2, 3. Right here is B. And then C is at 7. 3, 4, 5, 6, 7, 1. Here is C. That's our pre-image. Did I put a prime there? Why did I do that? Didn't mean to do that. And now we're going to translate it according to the rule first. And so we're going to move everything 5 units to the left, and then nothing happens in the y. It doesn't go up or down because there's nothing added or subtracted to that y. And so our translation would make us just go 5 units to the left. So A goes 1, 2, 3, 4, 5 and ends up at A prime. B is at 1, 2, 3, 4, 5, B prime. And C, 1, 2, 3, 4, 5, C prime. There you go. Done with the translation. And then it says reflect in the x-axis. Well, there's a reflection rule for the x-axis, isn't there? Right here. But isn't the x-axis a horizontal line? So you can use the rule if you want to, that's okay. But you can also just count because the x-axis is horizontal. And anytime you have a horizontal or a vertical line that you're reflecting over, you can just count. It's really okay. I prefer it. To me, it's a little bit easier, but you could do it with the rules if you want. A prime, if you count 1, 2 to the x-axis, so 1, 2 out the other side for A double prime. B is at 1, 2, 3 from the x-axis, so 1, 2, 3 double prime. Sorry, B double prime. C is 1 away, so 1 out the other side gives you C double prime. And there you have your composition. And that's what it looks like when you're done. You know, what I think we probably should do at this moment is actually run ABC prime or ABC prime through the rule and make sure that it actually does generate those points. But this video is going to be forever long if I do. So trust me, you can count if the line is horizontal or vertical. Because we want to talk about rotations. Rotations comes with rules also, and it's just a matter of picking the right rule and doing what it asks you to do. So we have this quadrilateral RSTU. There are its vertices, and we want to graph its image after a 270 rotation about the origin. Well, we have 3 rules, a 90 degree, a 180, and a 270, and those are the only 3 angles that I'm ever going to ask you to do in this class. You can rotate any number of degrees, but it does get complicated because there's really only 3 rules. So we're just exploring the idea together. So if we are to rotate 270, then we're going to choose to use the 270 rule. And what the 270 rule asks you to do is to flip-flop the values and turn the x value to its opposite. If it was positive, it'll be negative. If it's negative, it'll be positive. So we can start out by recognizing that R is at 3, 1. And so we want R prime. We have to switch the values and turn that x value to its negative or to its opposite. And so we'd have 1, negative 3. S lives at 5, 1. So S prime must live at 1, negative 5. T lives at 5, negative 3. And so T prime has to live at negative 3, negative 5. Remember, the y value that you moved over to the x place stays the same. This was negative 3, and so it will stay negative 3. But that x value that went into the y place has to turn to its opposite. That's how I got the negative 5. And then u lives at 2, negative 1. So u prime lives at negative 1, negative 2. You guessed it. And then we just have to throw these points onto the graph. So 1, negative 3, 1, negative 1, 2, 3 is where r prime is. And then we have 1, negative 5 for s prime. So there's 1, 1, 2, 3, 4, 5 for s prime. T is at negative 3, negative 1, 2, 3, 4, 5. So here's T prime. And then negative 1, negative 2 is where you live. Is where u prime lives. Negative 1, negative 2, u prime. It's a bummer you're not in class to hear all of my lame geometry jokes. But, you know, I insert them into the video when it makes sense. So now that we have connected all of those together, you can see that we have successfully rotated our STU around the origin 270 degrees. Boom, done. All right, then the last transformation we started talking about was dilations, and the first thing we talked about was whether or not you could find the scale factor of a dilation, and then if you could tell whether it was a reduction or an enlargement. Finding the scale factor was a matter of using this cute little formula right here, Cp prime over Cp. And so we can do that, first part. Our scale factor is going to be the distance between C and P prime, which in this case is 12, over the distance between C and P, which is 8. And so we have 12 over 8, which is about 1.5, if I'm not wrong. And then, if we want to tell whether the dilation is a reduction or an enlargement, we just need to look at the value of k. Well, notice that k is not between 0 and 1. It's definitely bigger than 1. And so this is an enlargement. Now you could probably tell that just by looking at how this went with those little safety pins, but that's how you can tell if you don't have the picture. If your dilation is between 0 and 1, it's a reduction. If it's bigger than 1, it's an enlargement. We can also perform dilations on graphs by using a dilation rule, and the dilation rule looks like take x and y and change it according to the scale factor by multiplying the scale factor by both the x and the y, generating new points, and then graphing them. So in other words, if k lives at negative 1, 2, then k prime must live, let's see, what's our scale factor? Oh, it's 3. So in this case, k is equal to 3. So we have 3 times negative 1, or negative 3, and 3 times 2, which is 6. L lives at 0, 2. So L prime must live at 0 times 3, which is 0. Why isn't my board working? I think I angered it. Might have to pause. Oh, come on now. This video's long enough. 0 times 3, or 0. And then 2 times 3, which is 6. All right, M is at 1, 1. So to find M prime, we just multiply both of those by 3 and get 3, 3. And N is at negative 1, 1. So we multiply both of those by 3 to get N prime, and we have negative 3, 3. And now we graph the new points. So we have negative 3, negative 1, 2, 3, positive 1, 2, 3, 4, 5, 6. This is K prime. We have 0, positive 1, 2, 3, 4, 5, 6 for L prime. We have 3, 3 for M prime. And then N prime is at negative 3, 3. And you can see that that has gotten 3 times bigger. That's how you dilate stuff, using the rule. Okay. By the way, you can also have negative scale factors, and they do something interesting. You follow the same rule. You take each point, and you multiply each piece by the scale factor. Whoops. So this time we have -2, which is our scale factor. So if f is at 3, 4, then f prime is at 3 times -2 or -6, 4 times -2 or -8. G is at 3, -3, so G prime is at 3 times -2, -6, -3 times -2 or +6, and then H, which is at 4, 4, goes to H prime, which is at -8, -8. Okay, and now we can graph those. -6, 1, 2, 3, 4, 5, 6, -1, 2, 3, 4, 5, 6, 7, 8. Way down here is f prime, -6, 1, 2, 3, 4, 5, 6, +6, 1, 2, 3, 4, 5, 6. Here is G prime, and then we have -8, -8 down here. It's going to be H prime. Oh boy. Alrighty. So interesting, isn't it? That negative scale factor doubled the size of the triangle just like we would expect, as if that negative sign wasn't even there. It made that triangle 2 times bigger. But the negative flipped that triangle around 180 degrees around the origin. And so, I don't know why that's there. What negative scale factors do is not only enlarge or reduce an object, but that negative sign throws it around the origin 180 degrees. It's sort of like a composition, but all in one step. All right, and then the last thing we talked about was similarity transformations, and friends, this is just a matter of understanding that when things change size, we can't call them congruent anymore. We have to call them similar. Well, when they dilate, when they follow a similarity transformation, things can change size without being similar. But what I mean is, if there's a dilation involved, you will have similar objects, objects that have congruent pairs of angles, but sides that change according to the scale factor. So we have this triangle, we're going to translate it, and then we're going to dilate it. So here we go. The translation says for us to move it 5 units to the right and 1 unit up. So let's do that business, shall we? A goes 5 units to the right, 1, 2, 3, 4, 5, and 1 unit up, boom. And we have A prime. And B goes 1, 2, 3, 4, 5, and 1 unit up for B prime. And C goes 1, 2, 3, 4, 5, and 1 unit up for C prime. And there is our translation. And now we want to dilate. And so we're going to have to take ABC prime, figure out its coordinates, and then dilate them by 2. So A lives at 1, 2, or sorry, A prime is at 1, 2. And so A double prime is going to be 2 times each of those. So 2 times 1 is 2, and 2 times 2 is 4, and we've got A double prime. B prime lives at 3, 3. And to get B double prime, we just have to multiply by the scale factor 2. And so we have 6, 6. And then C prime lives at 3, 2. And to get C double prime, we multiply each of those by 2, and we get 6, 4. Now we graph these new points. 2, 4 is here. 2, 1, 2, 3, 4. There is A double prime. Let's see, 6, 6. There's 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Here's B double prime. And then C double prime is at 6, 1, 2, 3, 4 right here. And there you go. There is your similarity transformation. The translation did not change the size, but the dilation did, and so we call it a similarity transformation. Well, all right, y'all. That is a quick, not so quick, review of the kinds of things you might see on the test. That test is going to drop on Monday, and so you have the weekend to watch this video and shore up your notes, make sure you've got what you need. This test is going to be open for 1 week. So please get in there and get that done this week. Just try your best. Remember, tests don't eat people. My grandmother says, do not fear that which cannot eat you. Tests don't eat people, y'all. Nothing to fear here. Tell me where you're at. If you do spectacularly terrible, that's just information for me, so I know how to help, okay? I believe in you. You got to believe, y'all. You can do this. I know you can. If I can do it, you can do it. Okay, you guys, have a wonderful day. Have a wonderful weekend, and I'll see you soon. Bye.